a scalar. Scalar is only got it's a quantity with only magnitude, and then a vector is a quantity. It's a one-dimensional structure with magnitude and direction, and then a matrix is a multi-dimensional vector, right? And then a tensor is a multi-dimensional matrix. And then if you recall, I think you guys did probably, this is what you do in what, form 2 or form 3 maths? Don't remember. So, and then let's talk about matrices. So if we've got an M by N two-dimensional array of values, so a matrix is normally an M by N two-dimensional array of values. Represents the number of rows and the number of columns. So matrix are referenced by two element subscripts. So the first element is subscript in the row. Sorry, I think this thing doesn't, yeah, so let me. So a matrix is referenced by two element subscripts. So this is the first element. So A11 is the first element. Then the second element would be A12 and A1n being the last. And then going down, you then have A21, A23, A3, 4, and AMN. Going row wise. So the first element in the subscript is in the the first element in the subscript in the row, this one A11. The second element in the subscript in the column, which is A12 up to A1n. So, for example, A24 or A24 is element in the second row, and it's in the second row a fourth column. Is this clear, guys?
Yes.
Yes, sir.
Right. So a vector can be regarded as a special case of a matrix where one of the matrix dimensions is equal to 1, right? So then a matrix. So let's look at the whiteboard. So a vector will be, in this case, one of the dimensions will be 1. So this is considered to be a vector, right? And this, so if we represent it by V, this is a vector, and this is also a vector. And remember, we said we denote it by M by N, where M is the number of rows. It's the number of rows, and N is the number of columns. right? So in this instance, this one we've got 1, 2, 3 rows and 1 column. So this is a 3 by 1 vector, right? Consider this is a 3 by 1 vector, and this one has got 1 row and 4 columns. So this is so we've got 1, 2, 3, 4 columns and 1 row. So this is a 1 by a 4 vector, right? So a vector, one of the dimensions has to be 1. So that's what we mean by one of the dimensions has to be 1. And then moving on, then a vector can be regarded as a special case of a matrix where one of the matrix dimensions is 1. So it's either when m or n is equal to 1, and then a matrix, a transpose is denoted by T, swaps rows, swaps columns and rows. Row 1 becomes 1 and column 1 and so on. So if so an m by n matrix becomes an n times m matrix. So in this so we've got, so if we've got so we said if we've got a matrix which is a 1, 1, a 2, 1, oh sorry, it's a 1, 1, 1, 2, a 1, 3 is, and then it's called a 1 4. Then this becomes a 2, 1, a 2, 2, a 2, 3, a 2, 4. So a 1, a 3, 2, a 3, 3, a 3, a 3, 4. So we denote the transpose of a matrix by a capital letter T. So when we transpose, so this is a 3. So this is remember we said m is the number of rows. So this is a 3, 1, 2, 3, a 3 by 4 matrix, right? A 3 by 4 matrix, and we've got 3 rows and 4 columns. So when we're doing a transpose of a matrix, we swap the values of m and n for each element within the matrix. So the transpose then will mean is equal to n by M. So what that means is A11 will become A11. It doesn't change. And then A112 becomes A21. And A13 becomes A31, and so on, right? So these values, this one goes there, this one comes here. This one remains where it is because A22 still remains as A22. A23 becomes A32, so this one goes here. A33 remains the same because A33 will remain the same. A34 becomes A43. So therefore this structure then changes from a 3x4 matrix to a 4x3 matrix. So it will have it will have 4 rows and three columns. So in this instance, then it will it will be A11 and A12 comes here. And A13 comes here. And A14 comes here. Then we've got A21 comes here. And A22 remains in the same position. And A23 comes here. And A24 comes here. And then A31 comes here. A32, and then A33, and then A34. So this is the transpose of a matrix. So this should be a straightforward. This is actually I believe, if I'm not mistaken, should be form in three maths. Right. So if you've got this matrix, for example, 2, 7 minus 1, 0, 3, 4, 6 minus 3, 1, 8, the transpose is equal to 2. So this is it's got 2 rows and 1, 2, 3, 4, 5 columns. So it's a 2x5 matrix, and the transpose will give us a 5x2 matrix. Are there any questions on this? This one. Which one? This one. Oh, this one, it's, yeah, it was supposed to be a part of another example, which was supposed to be removed anyway. Thanks for that. I've removed. It's not part of the. It's part of this. It's supposed to be a part of some example. Anyway, moving on. So if we've got an n by m matrix, if n is equal to m, then it's called a square matrix. So a 2 by 2 matrix is a square matrix. A 3 by 3 is a square matrix, and so on, right? And then the identity of a matrix is denoted by I, and its diagonal elements are 1 and while the others are 0. So the identity of a matrix, it has to be so we can so the identity of a matrix, right? The diagonal is all ones, and everywhere else is 0. It's donated by I, and its diagonal elements are 1, while all the others are 0. So it's like this. So we've got a 1. Let's say everywhere else is 0. 0, 1, 0, 0, 1. So this is a 3 by 3 matrix, and this is 0, and then this is 1. And the diagonal, which is this, is all ones, right? And everywhere else is 0. So this is called the identity of a matrix, right? And then moving on, so if we multiply a matrix by its identity, we still get the matrix, right? So so let's say we've got a matrix. We've got a matrix A 1 1, A 1 2, A 1 3, A 2 1, A 3 1, A 2 2, A 3 3 2. A 2 3, A 3 3. So if we have a matrix like this, and if we multiply it by its identity, right? So in this case, its identity will be this. We still get we still get the matrix. So if you multiply a matrix is identity, you still get the matrix. And if you multiply the inverse of a matrix by the matrix, you get the identity of the matrix, right? And then if this is Form 3 maths, is this clear for everyone? You're just catching up on some of the things that you guys need to remember, right?
Yes, it's clear, Doc.
So that we are clear. So let's say for example, we want to predict house prices, right? Let's say we want to predict house prices, right? So let's say the price of a house, right? The prices of a house, let's say we're choosing the variables for the price of a house. So let's say it's equal to some factor alpha 1 multiplied by the square, the size in square meters, right? One of the factors is possibly a size, which is the size of the size of land. And then the other one could be the number of rooms, yes? And then the other one could be a location, right? And then possibly the other one could be, does it have a Jura wall, right? And then the other one could be, for example, does it have a borehole? Yeah, so let's say these are the 5 variables. In machine learning, we refer to these variables as features. So let's say a house in. So what we then do then is for each. Let's say we've got the price of a house in. Yeah. So what we then do is we can then say. You can then write this in matrix notation. You can actually then write this as a price is equal to and we can put this as size and a number of rooms allocation. Natural. Does it have a wall? And does it have a ball? Right? And then we've got the parameters. Then we have alpha 1, 2, to alpha 5. Right. So if you multiply these two, they give you this above, right? So you find that a lot of the excuse me, a lot of the expressions and equations are actually written in matrix and vector and vector notation. Right. Moving on. So if addition is simple for matrices, you just add the matrices must be the same size and correspond, and you add the corresponding elements, and the result is a matrix of the same size. And a scalar multiplication of a matrix, you multiply each element by a scalar, and the result is a matrix of the same size multiplied multiplied by each element with the scalar. Then a matrix multiplication, a vector matrix multiplication is just a special case. So multiplication is associative. So A times bracket B times C is equal to B times is equal to A times B bracket times C. So multiplication is not commutative. So A times B is not equal to B times A. And then we have what we call the transposition rule, where we say A times B transpose is equal to B transpose times A transpose. So this is an example of a multiplication. So it's 1 times 2 times 1. Right? If we add 1 times 1, 2 by 1. So this is what the result will be, right? So this is normal multiplication. So we'll look at the other types of representation of multiplication as well. So you can have what is represented. So we'll talk about, so for example, if we've got A, what this means, A a circle with a dot in the middle. Is also a form of multiplication, but does anyone know what this is called? Come on, guys! How many guys here have done maths at university level or A level?
Isn't that a dot multiplication, though?
Yeah, exactly. That's the dot multiplication. Exactly. So the dot multiplication, what the dot multiplication does is it. So if we have So if we have A equal to A11, A12, A13, and then A21, A22, A23, E1, A32, and A33. So if we have our matrix A like this, and then we apply the dot product, and if we've got our matrix B, which is B 1 1, B 1 2, B 1 3, B 2 1, B 2 2, B 2 3, B B1, B2, and B 3 3. So the dot product of a matrix, what you do is you do it column wise, right? So I multiply. So we do it column wise. Like this, right? So we then have the first element being equal within the matrix, being equal to B, being equal to A11 multiplied by B11 plus B21, A21. So you multiply every column with the corresponding column value, right? And so this one will give you the first element, and then this, and then this B, and then you multiply this same one with first column with this for the next element. Right, and then you then move on to the next one, right? Right. Then after I do that, then I then take the second column. I multiply it with the first column to get the second element within the matrix, the second row of the element within the matrix. And then I then multiply this with that, with this, and with that, and then this one will be the last one, then I multiply with every other column within the other corresponding matrix. So this is what we mean by dot product. You see, we use that a lot when we are doing what are called convolutional neural networks, when we are doing a machine learning of images, when we're trying to do object identification and object recognition. So we'll do that when we're doing convolutional neural networks. So that's the dot product of a matrix. So which is another form of multiplication, right? So let's move on. Is that clear for everyone?
Clear, Doc.
Yeah. So let's move on and talk about vectors and matrix and norms. So the magnitude of a vector can be measured using a norm. So the norm of a matrix is used a lot in machine learning, especially in the old machine, the traditional, what we call the traditional machine learning and learning algorithms. They're all based on the norm of a vector. So norms map vectors to non-negative values. The norm of a vector x measures the distance of the origin to the point x. So the formal definition is we have what we call the LP norm, right? So coming here, let me push this up. Right, so we call it the LP norm of a vector. So this is defined as equal to this is represented by two double lines with an X and a P, and then a P is here. So it's represented like this, and so the formula is actually equal to the summation of the modulus of xi, right, to the power of p, right, and everything to the power of 1 over p, right? So this is called the LP norm of a vector. We'll get into the details and explain what that means, right? It's called the LP norm of a vector. So an LP of a vector x is an element of real numbers. Is defined as this. So it's these two double lines with x and equal to this. So let's give an example of when p is equal to 2. So if p is equal to 2, what that means is we've got x 2. So this becomes L2. And then it's equal to the summation of x I, and this becomes a squared, right, to the power of 1 over p, right? So let's say, for example, we since we're dealing, so when we're dealing with the norm, we're dealing with vectors. So let's say we've got yes. Yeah, it's a 2. So yes, that's a 2. That's correct. That is a 2. Absolutely, yes, that is a 2. So let's say, for example, we've got this point 2, 3, right? Right. This is the x-axis, right? And this is the y-axis, right? And this point, remember, we're measuring it. If it is a vector, we measure it from the point of origin, right? Yes, guys. And this is 2, and this is 3. So then the L2 norm of this vector is equal to the summation, right, of the modulus of 2 squared plus the modulus of 3 squared, right? And we take then 1 over p, which is 1 over 2. So this is then equal to 4 plus 9, the square root of this, yes, which is equal to the square root of 13. Yes, yes, guys.
Hello, Doc.
Yes.
So
Yes.
on this example, that is just a Euclidean distance that we have calculated.
Yeah, I'm getting there. So the L2 norm is equivalent. Yes, is equivalent to the Euclidean distance. Sequence. So if we do this, right? If I draw a straight line up to here, right? And then if I draw another straight line here like this. So one thing you find, so if this is 2 and this is 3, right? And if this is the square root of 13, or of 2 squared plus 3 squared, right? So this is also remember, this is from 3 maths or from 2 maths. This is also this is what this is a Pythagoras theorem, right? Yes.
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 Mhm.
Right. So this is Pythagoras theorem. So Euclidean distance is the same as what Pythagoras theorem, right? I think it's the same thing. So we're measuring the distance from the point of origin up to this point, right? So this is the diagonal of the triangle, right? And it gives you the Euclidean distance as well. Then you might ask, why is this why is this important? Why is this important? So let's talk about let's say, for example, so the difference with for example, you guys did regression analysis, right? Yeah, you guys did regression analysis, yes?
Yes.
Yes, we did.
Yes. So when you did regression analysis, you used the least squares method, right? Hello, guys.
Yes, Doc.
Some are saying no, some are saying yes. What's the answer? All right. So let's talk about the differences of between regression and machine learning. So if I have right. So if I have y, then if I have x like this, right, and then I've got my let's say these are my data points, right? Right. I've got my values of y and x, and this is just a scatter plot of, right? So this then represents, so these are the values that I'm plotting on here. Yes, this is straightforward. Yes. So in
Yes.
yeah. So what you normally do is in linear regression, you look at especially the least squares method. So what you're basically trying to do, if you did the theory of linear regression, you're trying to create a best line of fit that represents the data points, right?
Mm-hmm.
Yes. Yeah. So therefore, this becomes your model y represented by some alpha x plus some right. So therefore, this becomes your estimated your baseline of fit, which to fit the data points, right? Your baseline of fit to fit the data points, which represents your model, right? So in machine learning, the approach is completely different, right? So in machine learning, we are learning. We're not fitting a formula. We are learning what we call a representation of data. So in machine learning, we are learning a representation of data. And what do we mean by we're learning representation of data? So yeah. So what does that mean? So now the difference is I'm now looking at this. I'm looking at this point from the point of origin, right? And I'm looking at the L2 norm, right? And then I take this point from the point of origin. I'm looking at the L2 norm, and so on, right? So here I can extend this, and then I can put the L2 norm, right? And then it will give me the different L2 norms, right? So what that does is I now know the distance of each point, right, from the point of origin, right? I know the distance from, right? So if I know the distance so in this instance, I've got to make it clearer, right? To make it clearer is if I've got, let me just draw them as lines to make it easier. So if I've got a point here, right, that goes to the point of origin, and I've got another point here to the point of they're all going to the point of origin, right? And then I've got another point somewhere here. What this allows me to do is when I'm looking at the distances from the point of origin, it allows me to learn the representation by calculating the Euclidean distance of each point from the point of origin. Then I can then compare so if I do it like this, right, and then I can also do it like that. Right? So what I can now do is I can actually compare the marginal difference or the distances between these two points, right? Yes.
Yes.
If then I can actually know the distances between these different points. And what that does is, if I know the distances between these points, it's now easier for me to create the best possible line of fit for those different data points, right? Without plugging in a formula, just by looking at the Euclidean distance or the L2 norm of those points, right? So this is what machine learning is all about. So most of the machine learning models, they use some kind of L2, some kind of LP norm, right? It can be LP, it can be some kind of LP norm where P can be 2, where it can be Euclidean distance, it can be Manhattan distance, it can be some kind of distance, right? So this is a linear, for example, this will be a linear regression using machine learning. And then if we're then doing, for example, clustering or classification, we'll have, for example, we can have, for example, if it is clustering, so if it is, for example, clustering, let's say we've got three clusters. We've got cluster A, we've got cluster B, and then we've got cluster C, right? So now if we want to learn the representation of data, we still do the same thing by using some kind of LP norm calculation. So what we are simply doing is we're now looking at each the distance of each point from the point of origin, right? Then when we found the distance of each point from, it's easier for us to, then I can group the clusters which are similar and draw a circle, right, around all the points that are of a similar distance, right? I can draw all the different points. I can draw a circle around all the different points which are closer distance to, which are closely together, right? And then I can then with that we've identified 3 clusters. So what I can then do is I can then create what we call a decision boundary that separates the three clusters. So in this instance, I can then do something like this, right? So this line so I can then create a decision boundary, right? A line which separates the 3 classes. So therefore, this decision boundary then becomes my line that I can use to separate A, B, and C. So all machine learning algorithms are actually based on some kind of calculation using LP norm. This is why it's important to understand LP norm and understand vector notation and matrix notation. So if we look at, for example, algorithms like k-means, k nearest neighbors, support vector machines, right? So all of these algorithms, they all depend on using the some kind of LP norm, right? Is this clear?
Mm-hmm.
Yeah. So we're going to detail when we're talking about each one of these algorithms, right? We'll go into detail. But this is just showing you and explaining why you need to understand the LP norm, right? So if we go back, so when P is equal to 2, we get the Euclidean norm commonly known as L2 norm, which is the magnitude or distance in Euclidean space, commonly referred to this. For example, if x is equal to minus 1 and 2, then the L2 norm is equal to minus 1 squared plus 2 squared, which is equal to square root of 5, which is the distance of minus 1 to from the origin. Right? Is that clear? Yeah. When P is equal to 1, we get the L1 norm. Right? The L1 norm has the property of producing many coefficients with 0 values or very small values with few large coefficients. So the L1 norm increases as element of X increases. It is used to distinguish between the 0 and small values around the origin, which is very useful in machine learning. So a lot of these will actually make sense when we're actually looking at the machine learning algorithm, right? When P is equal to infinity, we get the L infinity norm, or the max norm, referred and frequently used in machine learning. It simplifies to the absolute value of the largest element in the vector, right? And then we've got what we call the Frobenius norm. The Frobenius norm is used to measure the size of a matrix, which is analogous to L2 norm form of a vector. So this is the formula for Frobenius Norm. So it is also used frequently in machine learning. So when we're now doing support vector machines, K nearest neighbor, K means, we'll then look at the different types of norms which are used to derive those machine learning algorithms. And then to normalize a vector, we divide the vector by the magnitude, right? So if the normalized vector, if you use vector divided by its norm, sorry, we divide by its magnitude. So to normalize a vector, we divide the vector by the magnitude. The normalized vector is a vector in the same direction, but the norm length is 1. It is also called a unit vector. So, for example, if we have a vector 0, 3 minus 4, the magnitude is the square root of 0 squared plus 3 squared plus minus 4 squared divided by 1, and then we multiply it by the actual vector, and then we get this value. So then this becomes the normalized vector. So when we're doing feature engineering, we'll talk about what we mean by we'll look at the different ways to scale. So it's a way of scaling your data. So you usually normalize data. So for example, if I go back to this example, so if we let's say if we're doing we want to predict we want to do regression to predict a GDP, for example, right? So the formula for GDP uses for values which are of different scales, right? So, for example, we can look at population size, right? The population size will be in millions, right? And then we can then look at the performance of the economy, and then the performance of the economy will be in hundreds of billions, right? So because those two values are of different scales, you want when you want to try and represent them on a two-dimensional graph, right? It then becomes very difficult to see the 2 points. So what then happens is for us to be able to visualize the 2 points and allow our algorithm to look at these points in the same scale. This is why we have to then normalize the our data points so that all the values, at least they are within the same range. So we'll do that when we're doing feature engineering, right? Yeah, right. So if we move on, so we denote an attribute of a vector as an italic value with an index like this. So we can call it WJ or XJ. And then if we move on to a set notation, a set is an ordered collection of unique elements denoted by S. A set of numbers can be finite, or the representation can be like this: x1, x2, x3, and so on. A set can be infinite and include all values in some interval. If a set includes all values between A and B, it will be written in square brackets like this. Say A and B. We use square brackets to denote it. So what I'll do is I'll give this so that you guys understand the notation. And normally we go through this notation when we're actually doing the algorithms, but it's important just to look at the maths behind behind machine learning, so that when we are doing some of the notation, we would have covered at least some introduction to the notations, and we would have done something in terms of scalars, vectors, matrices, and tensors, right? Yeah. So this is it as an introduction to the notation that we use in machine learning. But the thing is, you guys, you didn't do you didn't do a probability theory, so it's gonna be yeah, it's gonna be a bit of a challenge to talk about it's going to be a challenge to talk about the some of the things that probability theory for machine learning. But anyway, let's we'll be going on for 1 hour 30 minutes. Are there any questions so far? Guys, are there any questions so far?
So far, so good.
Yeah, so don't worry about so don't worry too much about this. We will cover a lot of this when we're actually doing the algorithms one by one.
Okay.
All right, shall we? So we've been going on for 1 hour 30 minutes. Shall we take a break, because the next lecture is going to be quite long. So shall we come back at 1:45?
Yeah, good idea.
All right, Doc.
It
Yes.
could be what?
11:45?